How does a car keep me and others safe in a crash? In this experiment, we will be designing a system that will replicate car safety features by protecting a water balloon. Before we start designing our car safety prototype, we must understand the most common car safety features used in car crashes. Car safety features have certainly evolved over many years, and drivers today are less likely to experience permanent damage due to car crashes. Some of the most essential car safety features include an electronic stability control system to help maintain control of the car in hazardous situations, curtain airbags for side protection to the head, and an automatic emergency braking system. There are many more innovations implemented into cars to use during the car crash itself, such as a crumple zone, seat belts, and strong occupant compartments. It is also essential that we understand what is momentum and impulse. Momentum is basically referring to the quantity of motion an object has. It is referred to through the formula P equals mv, meaning that momentum is the product of the mass of an object in relation to its velocity. Impulse is the change of momentum of an object when the object is acted upon by a force for an interval of time. It is expressed through the formula P equals Ft, meaning that impulse is the product of the force acting on an object in relation to its time. Based on our resources and time constraints, the car safety feature we settled on adopting was the crumple zone design. The whole purpose of it is that during a collision, to increase the time over which a change in velocity or momentum will occur, this will significantly reduce the impact in which the car driver and passengers face. The crumple zone I initially designed our first prototype as a 3D model, but due to 3D printing delays and errors, we could not come around to having this model ready to go. Instead, we created a rough prototype made of paper to quickly match our idea. The premise was to assess if our idea had the possibility of working out, as well as saving money for our next prototype. The paper model was a little bit flimsy and light, and it had some inconsistent dimensions. Overall, this design seems to be a very good initial concept. As shown in this slow motion video, the prototype was falling from a curved angle, and once the collision to the ground was made, the crumple zone did crumple but fell completely flat to the ground, allowing the balloon to be in direct impact with the floor, destroying its purpose. The prototype then tipped over and flipped over and then fell to its side. If the balloon were inside, it will not survive based on this test. The prototype weighed 0.44945 kilograms, and it took 0.62 seconds for it to drop in a 3-meter distance. It takes 0.21 seconds for it to come to rest after the collision. In this prototype, we had to calculate what was the momentum of the prototype, as well as determine the impulse. In order to calculate momentum and impulse, we must first start with Newton's second law, which is force is equal to mass times acceleration. Acceleration can also be expressed as change in velocity divided by time. So this creates the new equation of force equals mass times velocity divided by time. And when we multiply it by the time, it becomes force times time is equal to mass times change in velocity. The left side of the equation is impulse, and the right side of the equation represents momentum change. Now the equation for momentum is P equals mv, or momentum is equal to mass times velocity. So we must first calculate the velocity of the prototype. The distance was 3 meters, and it took 0.62 seconds for the object to touch the ground, so 3 divided by 0.62 is 4.839 meters a second. Then we take the mass of the object and multiply the velocity by that, which makes 0.44945 kilograms times 4.839 meters a second, which gives us a momentum of 2.1749 kilogram meters a second. Now this was the first momentum or the momentum of the object as it was falling down initially. Now to calculate the impulse, we must understand that impulse is the momentum of the object after an external force was acted upon it. So to calculate the velocity of the object traveled 15 centimeters or 0.15 meters within a span of 0.21 seconds, meaning that the velocity is 0.714 meters a second. Then multiplying the mass 0.4495 by the velocity makes 0.321 kilogram meters a second. Now that we know the velocity of the second momentum, we have to calculate the impulse by using the formula we talked about from the beginning. Impulse is equal to the mass times the elapsed time, meaning 0.44945, times 0.714, meaning the impulse is 0.321 newtons seconds. In order to find the force, we simply divide the impulse by the time, giving us a force of 1.529 newtons. Now the countering force, which changed the momentum of the object as stated in the law of conservation of mass, had a force of 1.529 newtons, and the change in momentum after that force was exerted was 0.321 kilogram meters a second. This means that the momentum really did decrease after the collision, but what really hurt the design was the model's instability. Next time we must 3D print the model to be sturdy and allow our crumple zone. Prototype 2 was 3D printed and as shown had a much lower height overall compared to the original 3D model of Prototype 1. The funnel was redesigned to be purposely destructible and to replicate the crumple zone of a car by adding holes to the funnel, making it more susceptible to crumple. However, the balloon had to remain secure inside the cockpit to keep it from falling by having secure occupant compartments. After placing the balloon in the cockpit, we placed some cotton balls in the side to give some cushioning, then we cut out a piece of paper and taped it up to finally seal everything up and close the cockpit. This drop has gone astonishingly well. The water balloon was able to withstand the drop without any damage to it. The prototype fell and the crumple zone broke apart into pieces. It took much longer time for the prototype to change its momentum, so it was able to help the balloon avoid such a collision. After the initial impact, the funnel was obliterated. With a mass of 0.27104 kilograms, the prototype collided at 0.53 seconds over a distance of 7 meters. Also, after the collision, or once a force acted against the object, the elapsed time was 0.3 seconds. Now to make our calculations. Going back to our original equation, we need to calculate the velocity to calculate the momentum of the object while it is in motion, so the object took 0.53 seconds to travel 7 meters, meaning the velocity is 13.208 meters a second. Plug it into P equals mv, the mass of the object, which is 0.27104 times 0.385 meters a second, will give us a momentum of 3.58 kilogram meters a second, which is quite a large force. Then to get our impulse or the change in velocity after the force of the ground was exerted, we take the distance of 5 centimeters or 0.05 meters and divide it by the elapsed time of 0.13 seconds, we get 0.385 meters a second. Then plug in the values into the momentum formula. 0.27104 kilograms times 0.385 makes 0.104 kilogram meters a second. Now to check our impulse again, we solve the formula Ft equals mv, where we multiply the mass by the velocity again, we get 0.104 newtons seconds. Then we divide the impulse by the time of 0.13 seconds, we get a force exerted by the ground of 0.8 newtons. It seems as if the impulse of this prototype was not that huge, considering most of the bottom fell completely obliterated and fell into pieces. And that is a huge safety hazard, especially if it were with cars. If all the parts that were destroyed flew everywhere, people could get hurt from this, so we must find a way to significantly decrease the momentum. Overall, the prototype that was the most successful was obviously Prototype 2. The water balloon survived and our intentions for the test to go went well. A modification we should have made for this prototype was to add a parachute to the model to further reduce its momentum. By adding parachutes to the model using air resistance, it will be a force acting against the model to decrease its velocity. This is used in different types of cars such as dragsters. This way the prototype will not completely obliterate and have pieces flying everywhere, but will have a parachute decreasing that momentum as well as still having the crumple zone in case the parachute fails.